Finding roots via the zero product property. Welcome, everyone. Today, we are moving into the final stage of solving quadratic equations. Now, you have already learned the hard work of factorizing, breaking down a complex quadratic expression into its simpler parts. But once you have successfully factorized that equation, your work isn't quite finished. The ultimate goal, our final objective, is to actually determine the specific numerical values of x that make the entire equation true. These are what we call the roots. To bridge the gap between having a factorized expression and finding those actual values, we are going to use a fundamental algebraic principle called the zero product property. In the next few slides, I will show you exactly how this property works and how you can use it to solve any quadratic equation with confidence. Understanding the zero product property. Now that we know our ultimate goal is to find the actual values of x, let's dive into the logic that makes this possible. We are going to look at the zero product property. You can think of this property as a simple but incredibly powerful logical rule. It states that if you multiply two or more real numbers together and the resulting product is zero, then at least one of those individual numbers must be zero. There is no other way to get a product of zero. To put this into mathematical terms, if we say a times b equals 0, then we can conclude that either a equals 0 or b equals 0, or in some cases, both a and b are 0. Now, how does this apply to the quadratic equations we've been working on? Well, when we successfully factorize a quadratic equation, we are essentially transforming a complex quadratic expression into a product of two simpler, linear expressions. For example, let's look at this equation. Px plus q, all inside a bracket, multiplied by rx plus s, all inside a bracket, equals 0. In this scenario, we can treat the entire first bracket, px plus q, as our a, and the second bracket, rx plus s, as our b. Applying the zero product property here, we can see that for this entire product to equal 0, the logic dictates that either the first bracket must equal 0, or the second bracket must equal 0. This is the key insight that allows us to break one difficult equation down into two much simpler ones, which we will walk through step by step in the next slide. Step-by-step process to find the roots. Now that we understand the logic behind the zero product property from the previous slide, let's look at the practical, step-by-step process you should follow to actually find those roots. Once you have successfully reached the factorized form of your quadratic equation, you aren't finished yet. You now need to follow these 4 steps. Step 1, your first task is to set each linear factor to 0. This means you take each individual bracket and create two separate, simpler linear equations by setting them equal to 0. In mathematical terms, you are saying that p times x plus q equals 0, or r times x plus s equals 0. Step 2, next, we solve the first of these linear equations. Your goal here is to isolate x. You do this by moving the constant term to the right side of the equals sign, remembering to change its sign, and then dividing by the coefficient of x, so p times x equals negative q, which ultimately gives us x equals negative q divided by p. Step 3, now, we simply repeat that exact same process for the second factor. You'll take r times x plus s equals 0, move the s to the right to get r times x equals negative s, and finally, divide to find that x equals negative s divided by r. Step 4, finally, you state your final roots. The two specific values you just calculated in Step 2 and Step 3 are your roots, which are also known as the solutions to the quadratic equation. In the next slide, I will show you exactly how this looks in practice with some concrete examples. Illustrative examples. Now that we have covered the theory and the step-by-step process, let's put everything we've learned into practice with some illustrative examples. First, let's look at example 1, which is a pure algebraic equation. Here, we are asked to solve for x, given the equation 2x minus 3, all in brackets, multiplied by x plus 5, all in brackets, equals 0. To solve this, we follow the steps we discussed in the previous slide. Step 1, we apply the zero product property. Since the product of these two brackets is 0, we know that either the first bracket, 2x minus 3, must equal 0, or the second bracket, x plus 5, must equal 0. Step 2, let's solve that first linear equation. If 2x minus 3 equals 0, we move the negative 3 to the right side, making it 2x equals 3. Then, we divide both sides by 2, which gives us x equals 3 over 2. Step 3, now we solve the second equation. If x plus 5 equals 0, we subtract 5 from both sides, leaving us with x equals negative 5. So, our final answer for this algebraic problem is that the roots of the equation are x equals 3 halves and x equals negative 5. Now, let's move on to example 2, which shows how we apply this in a physical context. Imagine we have a rectangular plot, and its area is represented by the quadratic equation, x squared plus 2x minus 24 equals 0. After we have performed the factorization process, we are left with the equation, x plus 6, in brackets, multiplied by x minus 4, in brackets, equals 0. We follow the same logic here. Step 1, apply the zero product property by setting each factor to 0. This gives us x plus 6 equals 0, or x minus 4 equals 0. Step 2, we solve for x from the first factor, x plus 6 equals 0, we find that x equals negative 6. From the second factor, x minus 4 equals 0, we find that x equals 4. However, step 3 is crucial in real-world problems. We must evaluate the physical validity of our answers. Since we are dealing with the dimensions of a physical plot, a length cannot be a negative value. Therefore, we must discard the root x equals negative 6. This leaves us with our final answer. The only valid physical root is x equals 4. As we move to the next slide, keep in mind that while the math might give you two answers, the context of the problem determines which one is actually usable. Common mistakes to avoid. First, let's talk about what I call the stopping error. This is perhaps the most frequent mistake I see. After you have done the hard work of factorizing a quadratic, you might find yourself looking at something like x minus 3, all in brackets, times x plus 2, all in brackets, equals 0, and thinking, great, I'm done. But remember, the goal isn't just to factorize, the goal is to find the roots. The factors themselves are not the answers. You must take that final extra step to actually solve for x. Next, keep a very close eye on your signs. This is a classic area for simple errors. When you move a constant term from the left-hand side to the right-hand side of the equation, you must change its sign. For instance, if you're working with the factor x plus 5, and you set it to 0, moving that positive 5 across the equals sign turns it into a negative 5. So your root is x equals negative 5, not x equals 5. A small slip here can change your entire final answer. Finally, be careful with your division. When you reach the stage where you have something like 2x equals 3, don't accidentally subtract the 2 from the 3. You must isolate x by dividing both sides by the coefficient, which is 2. This gives you the correct root of x equals 3 over 2. Now, before we wrap up today's lesson with our final summary, I want to pause and discuss some common pitfalls. Even if you have mastered the logic of the zero product property, there are a few trapdoors that students often fall into during exams. If you can avoid these 3 mistakes, you'll be well on your way to mastering this topic. Now, let's move to our final slide to review the key takeaways. Key takeaways. First, let's revisit the core logic that drives this entire process, the zero product property. Remember, the fundamental idea is that if the product of two factors is 0, then at least one of those individual factors must be 0. This is the magic that allows us to move forward. Second, think about the transformation we are performing. By using this property, we are essentially taking one complex quadratic equation and breaking it down into two much simpler, manageable linear equations. We are turning a difficult problem into two easy ones. Third, always keep the ultimate goal in mind. We don't factorize just for the sake of it. The entire purpose of factorizing a quadratic is to use this property to isolate and find the actual values of x, which we call the roots. Finally, a very important reminder. context matters. As we saw in our second example with the rectangular plot, math doesn't exist in a vacuum. When you are solving real-world problems, always take a step back and check if your mathematical answers make physical sense. If you calculate a negative value for a length or an area, you must discard that root, as a negative dimension is impossible in the real world. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways to ensure you have a solid grasp of everything we've covered today. Now, as long as you remember these points and avoid the common pitfalls we discussed earlier, you'll be able to master finding roots with confidence. Great job today.